Hello guys! We are going to talk about the angular modulation, specifically on frequency modulation or FM and phase modulation PM. I am Gian Duhina from class ECA 111 B15 of Communications 1 Principles of Communication Systems. The frequency modulation or FM uses the information signal which varies the carrier frequency within some small range about its original value. FM radio uses frequency modulation. The frequency band for FM radio is about 88 to 108 MHz. The information signal is music and voice which falls in the audio spectrum. The full audio spectrum ranges from 20 to 20 kHz, but FM radio limits the upper modulating frequency to 15 kHz, although some of the signal may be lost above 15 kHz. Most people can't hear it anyway, so there is little loss of fidelity. FM radio may be appropriately referred to as high fidelity. Phase modulation or PM can be used for both analog and digital data, but it is for data and phase shift keying that is most widely used. It uses variation in phase for carrying the modulation. As phase and frequency are interrelated, this relationship carries forwards into phase modulation, where it has many commonalities. And with frequency modulation, as a result, the term angle modulation is often used to describe both. Phase modulation or PM is used for analog transmissions, but it has become the basis for modulation schemes used for carrying data. Comparing the frequency modulation to phase modulations both are proportional to modulating signal. Frequency modulation is more superior to the PM. Signal to noise ratio or SNR is better than in PM. It is widely used for commercial broadcast radio such as 88 MHz to 108 MHz, and its modulation index is proportional to modulating signal as well as modulating frequency. While as in phase modulation, noise immunity is better than AM but not in FM. Signal to noise ratio or SNR is not as good as in FM. PM is primarily for some mobile radio services. And last, modulation index is proportional to modulating signal. The comparison of FM or PM to angular modulation are frequency modulation receivers have better noise immunity, while amplitude modulation receivers are very susceptible to noise. Frequency modulation noise immunity can be improved by increasing the frequency deviation, while in AM, no such option exists in AM. FM bandwidth requirement is greater and depends upon modulation index, while the AM bandwidth is less than FM or PM and thus doesn't depend upon modulation index. FM or PM transmitters and receivers are more complex than for AM, while AM transmitters and receivers are less complex than for FM or PM. FM, all transmitted power is useful, so FM is very efficient, while in AM, power is wasted in transmitting the carrier and double sidebands in DSB, but DSB SC addresses like this. Here are some equations that we'll be needing for calculating the frequency modulation FM and phase modulation PM, and as well as a pictorial way to view the generation of FM and PM. The frequency modulation index is the equivalent of the modulation index for angular modulation or AM, but obviously related to FM. In view of the differences between the two forms of modulation, the FM modulation index is measured in a different way. The FM modulation index is equal to the ratio of the frequency deviation to to the modulating frequency. To give an example of the FM modulation index, take the example where a signal has a deviation of 5 kHz and the modulating frequency is 1 kHz. Then the modulation index for this particular instance is 5 all over 1 is equals to 5. Similarly, if the deviation is 10 plus 10 kHz and the modulating frequency is S kHz, then this also has a deviation of 5. Adding the baseband signal itself rather than the integral of the baseband signal, it causes the phase to vary according to the baseband value. Thus, phase modulation is actually a bit simpler than frequency modulation. As with the frequency modulation, we can use the modulation index to make the phase variation more sensitive to the changes in the baseband value. The similarity between phase modulation and frequency modulation becomes clear if we consider a signal frequency-based baseband signal. The integral is simply a time-shifted version of the original signal. Thus, if we perform phase modulation and frequency modulation with this baseband signal, the only difference in the modulated waveforms will be the alignment between the baseband value and the variations in the carrier. The variations themselves are the same. The percent modulation is defined as the ratio of the actual frequency deviation produced by the modulating signal to the maximum allowable frequency deviation. So for the frequency modulation or FM is stated for the frequency deviation as KF, where it is a sensitivity constant. The units are in radians all over volt minus sec. While as in phase modulation or in PM, the phase deviation is stated as Kp, a sensitivity constant. Its units are in radians all over volt, while actually in radians over unit of the parameter mt. Another equations that will be helpful for the frequency deviations are equations for the FM wave with single tone modulation. As you can see, the deviation sensitivity as stated as Kf and frequency deviation as the delta F is equals to Kf AM or is equal in Kf times the M max minus M minimum all over 2 times 2 pi. The frequency modulation equation will be using a Bessel function. The Bessel function identities above can be found in Abramowitz and Stegan. And now the proof, we start with this equation. And to apply the sum identity for the cosines to get this equation. Now, let's take the first term of this equation. And apply one of our Bessel identities to expand it to which can be simplified to this equation. Where the sum runs over all even integers, positive and negative. Now, we do the same with the second half of the cosine sum. We expand this equation to which simplifies this equation to where again the sum is overall at this time integers. Combining two halves gives us our result. For practical bandwidth calculation for frequency modulation or FM, we will be using the wideband FM with the Carson's rule.